All right, so far we talked about how we can learn value functions represented in a tabular form. So there's no neural net, no deep RL, no function approximation, just a small discrete state space where we can enumerate the value in every possible state. Now let's talk about how we can introduce neural networks and function approximation. So first, how do we represent V of S? Well, so far we talked about how we can represent it as a big table with one entry for each discrete state. So in state 0, you say V of S is 0.2, in state S equals 1, it's 0.3, and so on. Why is this not enough? Well, take a moment to think about this. Why might we not want to represent the value function as a table? Let's say that you're playing a video game from images, right? Now, in this video game, the number of possible states, if you have a 200 by 200 pixel image, is 255, which is the number of values that each pixel can take on, raised to the third power because there are 3 color channels, raised to the power 200 times 200. So this is the number of possible images you could see. Maintaining a table over this many entries is impossible. This is more than the number of atoms in the universe, and that's for a discrete state space. For a continuous state space, it's actually just infinite, and this would never be possible. And this is also, by the way, sometimes referred to as the curse of dimensionality. If someone says curse of dimensionality in the context of reinforcement learning, what that refers to is the simple fact that if you have a state space with many dimensions, the number of entries that you need in a table for tabular reinforcement learning is exponential in the number of dimensions. So we'll use a function approximator. Let's say just like in lecture 6, we're going to have a neural net value function that maps from states to scalar valued values. So we're going to have a neural net that looks like this. And it has some parameters phi. So what we can do is we can fit our neural net value function in much the same way as we did in lecture 6 by doing least squares regression onto target values. And if we use the value iteration procedure from the previous section, then our target values are just the max over A of Q pi SA. So then our fitted value iteration algorithm would look like this. We would take our data set of states and actions. For every sampled state, we would evaluate every possible action you could take in that state, and we would take a max over those actions of our Q values. So what I have in the parentheses here is I've just substituted in the Q value. So the Q value is the reward plus gamma times the expected value of the next state. So I've substituted that into the parameters. We don't represent the Q function explicitly here. We just compute it as we go to evaluate the max. And that gives us our target values y. And then we solve for phi by doing least squares regression so that v phi of si is close to yi. So this is fitted value iteration. Step 1, compute your target values by constructing the Q function for every possible action at each sampled state. So you have a finite sampling of states, and we still assume that we have a discrete action space, so we can perform this enumeration exactly. For every action, we evaluate its reward, plus gamma times the expected value of the value at the next state. Do the max over that, that gives us our target value, and then in step 2, regress onto those target values. All right, so this is a reasonable algorithm that we could use, but it still requires us to know the transition dynamics. Where do we need to know the transition dynamics? Which part of this algorithm requires knowing the transition dynamics? Well, it's basically this part. So there are 2 ways in which this requires knowledge of the transition dynamics. It requires being able to compute that expected value, and perhaps more importantly, it requires us to be able to try multiple different actions from the same state, which we can't do in general if we can only run policies in the environment instead of teleporting to a state multiple times and trying multiple actions from the same exact state. So if we don't know the transition dynamics, generally we can't do this. So let's go back to policy iteration. In policy iteration, we alternated between evaluating Q pi, or A pi, but if you have A pi, or if you have Q pi, you can recover A pi. And then step 2, setting our policy to be this greedy argmax policy. So that was policy iteration. And step 1 in policy iteration involved policy evaluation, which involved repeatedly applying this value function recurrence that we saw before. So what if instead of applying the value function recurrence to learn the value function, we instead directly constructed a Q function recurrence in an analogous way? So if I wanted to construct the Q function at a particular state action tuple, I can write exactly the same recurrence, except that now, since the Q function is a function of a state and an action, I don't need to evaluate the next state given S and pi of S. I just evaluate the next state given the SA tuple that I'm training my Q function on. And this might at first seem like a very subtle difference, but it's a very, very important one. Because now, as my policy pi changes, the action for which I need to sample S prime, basically the A that's on the right of the conditioning bar and P of S prime given SA, doesn't actually change. Which means that if I have a bunch of samples, S, comma A, comma S prime, I can use those samples to fit my Q function regardless of what policy I have. The only place where the policy shows up is as an argument to the Q function at the state S prime inside of the expectation. And it turns out that this seemingly very simple change allows us to perform policy iteration style algorithms without actually knowing the transition dynamics, just by sampling some SA S prime tuples, which we can get by running any policy we want. So this second recurrence that I've written here doesn't require knowing the transition probabilities, it just requires samples of the form S, comma A, comma S prime. So if we do this for step 1 in policy iteration, we would no longer require knowing the transition probabilities. And this is very important. This is the basis of most value-based model-free RL algorithms. All right, now we seemingly took a step back because before we derived policy iteration and then we simplified it to get value iteration. And the way that we got value iteration is by using this max trick. In value iteration, we saw that when we construct the policy, we take the argmax, but then we simply take the value of that argmax action. So evaluating the value of the argmax is just like taking the max. So we can forego policy construction. We can basically forego that step 2 and directly perform value iteration. Can we do the same max trick with Q functions? So can we essentially do something like value iteration, but without knowing the transition probabilities? So what we did before is we took policy iteration, which alternates between evaluating the value function in step 2 and setting the policy to be the greedy policy in evaluating the value function in step 1 and setting the policy to be the greedy policy in step 2. And we transformed to this other algorithm where step 1 constructs target values by taking a max over the Q values, and step 2 fits a new value function to those target values. So here we forgot the policy, we just compute the values directly. So can we do this with Q values also, but still retain this benefit of not needing to know the transitions? So the way that we construct a fitted Q iteration algorithm is very much analogous to fitted value iteration. We construct our target value yi as the reward at a sampled state action tuple SI-AI plus gamma times the expected value of the value function at state S prime. And then in step 2, we simply regress our Q function Q phi onto those target values. The trick, of course, is that we have to evaluate step 1 without knowing the transition probabilities. So we're going to do two things. First, we're going to replace V of Si prime with the max over A at Q phi, Si prime, Ai prime, because we're only approximating Q phi, we're not approximating V phi. And second, instead of taking a full expectation over all possible next states, we're going to use the sampled state Si prime that we got when we generated that sample. And now all we need to run this fitted Q iteration algorithm is samples Si, Ai, Si prime, which can be constructed by rolling out our policy. So this is fitted Q iteration. It alternates between two steps. Step 1, estimate target values, which you can do using only samples and your previous Q function Q phi. Step 2, fit a new phi with regression onto your target values using the same exact samples that you used to compute your target values. And this doesn't require simulation of different actions, it only requires the actions that you actually sampled last time when you ran your policy. So this works even for off-policy samples, so this algorithm does not make any assumptions that the actions were actually sampled from the latest policy. The actions could have been sampled from anything. So you can store all the data you've collected so far, it doesn't need to come from your latest policy, unlike ActorCritic where we had an on-policy algorithm. There's only one network, there's no policy gradient at all, there's no actor, there's only a Q-function estimator, which is a neural network that takes in a state and an action and outputs a scalar valued Q value. Unfortunately, it turns out that this procedure does not have any convergence guarantees for nonlinear function approximation. So if you do this with a neural net, it may not converge to the true solution, and we'll discuss this a lot more later in the lecture. If you use a tabular representation, it is actually guaranteed to converge. But for a neural network, it's in general not guaranteed to converge. All right, so just to put the pieces together, here's the full fitted Q iteration algorithm. And for each step of the algorithm, there are some free parameters that I'm going to mention. Step 1, collect a data set consisting of tuples Si, Ai, Si prime, and Ri using some policy. The algorithm works for a wide range of different policies. Now, not all policy choices are equally good, but the principles will apply to any policy, and it certainly doesn't have to be the latest policy. And one of the parameters that you have to choose is the number of such transitions you're going to collect. So typically, you would roll out your policy for some number of steps or some number of trajectories, but you get to choose how many. And of course, you also choose the policy that you're going to be rolling out. What policy do you use to collect this data? A very common choice is, in fact, to use the latest policy, but there are a few nuances about that choice that I'll discuss shortly. Step 2, for every transition that you sampled, calculate a target value. So you calculate the target value yi by taking the reward from the transition plus gamma times the max over the next action ai prime of the Q value Q phi Si prime ai prime, using your previous Q function estimator Q phi. Step 3, train a new Q function, which means find a new parameter vector phi, by minimizing the difference between the values of Q phi Si ai and the corresponding target value yi. So you have a Q function which takes as input S and A, it outputs a scalar value, and it has parameters phi. I should mention, by the way, that a very common design for a neural network architecture for a Q function with discrete actions is actually to have the actions be outputs rather than inputs. So an alternative design is to input the state S and then output a different Q value for every possible action A. You can think of that as a special case of this design, and I'll discuss in class a little bit how those relate. But conceptually, it's probably easiest to think about as a neural network that takes S and A as input and outputs a value, but you could also think of it as a network that takes S as input and outputs a different value for every possible A. So in step 3, one parameter you have to choose is the number of gradient steps, capital S, that you will make in performing this optimization. You could run this optimization all the way to convergence, or you can run it for just a few gradient steps. Now, doing step 3 once doesn't actually get you the best possible Q function. You could alternate step 2 and step 3 some number of times, let's say capital K times, before going out and collecting more data. And the number of times you alternate step 2 and step 3 we're going to refer to as K. That's the number of iterations of fitted Q iteration that you take in the inner loop. And then once you've taken those K iterations, maybe you could take your latest policy, modify it with some exploration rules, which I'll discuss shortly, and use it to collect some more data. So this is the general design of fitted Q iteration. Many different algorithms can actually be interpreted as variants of fitted Q iteration, including algorithms like Q-learning, which I will cover shortly. All right, so to review this portion of the lecture, we discussed value-based methods. Value-based methods do not learn a policy explicitly, they just learn a value function or a Q function represented as a table or a neural network. If we have a value function, we can recover a policy by using the argmax policy. We talked about how fit acute iteration removes the need for us to need to know the transition probabilities, and we discussed this kind of generic form of the fit acute iteration algorithm.